So here we go. Once again, I Ajay Jha on behalf of ACS India team. Welcome you to today's ACS Science Talk session. Just to update you on the upcoming ACS Science Talk, please visit our ACS in India webpage and register for the upcoming sessions. We have also updated the past lecture recordings on the ACS Science Talk virtual library. Please feel free to visit, like, subscribe, and share among the scientific community. So we have the 10th DST and ACS workshop coming up featuring Professor Saras Karabulak, the editor-in-chief of Chemistry of Materials and ACS Material Letters. So register for this particular session and by visiting our ACS in India webpage. To keep you updated with the new latest findings on research and the latest events and product launches at ACS, we have a newsletter, ACS Insights India. Subscribe today for free. Here is a subscription link. We'll provide it into the chat box later. To begin with the scientific session, it's a pleasure and honor to have Professor Manish Chowalla with us. So Professor Chowalla is the Goldsmith Professor of Material Science at the University of Cambridge. Previously, he was a distinguished professor at Rutgers University in New Jersey, USA. He was also the director of the Institute of Advanced Materials, Devices and Nanotechnology at Rutgers. Professor Chowalla obtained his PhD from the Electrical Engineering Department at the University of Cambridge and Churchill College. After his doctorate and Royal Academy of Engineering postdoctoral fellowship, Professor Chowalla briefly worked in industry where he developed applications for amorphous diamond. He's an expert on optical and electronic properties of atomically thin two-dimensional transition metal dichalcogenides for application in field-effective transistors, catalysis, and energy storage. Professor Chowalla is the recipient of numerous awards and fellowship, including Fellowship of the Material Research Society, Institute of Physics, the Royal Society of Chemistry, and Churchill College. He was the founding editor-in-chief of Applied Materials Today and is now the associate editor of ACS Nano. In addition, he holds editorial advisory board position in several journals of international repute. With over 78,000 citations and H-index over 105, Professor Chowalla has been on the Clarivate highly cited researchers since 2016. Now I would like to invite Professor Chowalla to deliver his talk. I'll stop sharing from my end. Over to Professor Chowalla.
Okay. Thank you very much, Ajay, and your team for the kind invitation and the introduction. So today I'll talk about the versatility of metallic phases of two-dimensional transition metal dichalcogenides. We've been working on these metallic phases for the last 10 years, and we're quite surprised at their interesting properties. So this presentation, the technical part of the presentation, will be more of a kind of a highlight reel of some of the interesting properties of these 2D materials. But before I begin that, I would like to just tell you a little bit about ACS Nano. So I'm one of the editors at ACS Nano, and I handle papers that are mostly in two-dimensional materials, as you would expect, but also papers relating to catalysis and energy storage. ACS Nano is growing very rapidly in the sense that the number of submissions that we get increases by a substantial amount almost every week. The wonderful thing about ACS journals in general is that the editors are academics like you and I. So we're sort of experts in the field. We know we have our fingers on the pulse of the field. And the reason why that's important is because we're able to really judge papers that are, groundbreaking and transformative. So oftentimes these high-impact journals, Nature and Science and others, have professional editors where if something is truly groundbreaking, they may not. Those editors may not be able to sort of recognize that because it could be a risky publication. But as sort of experts in the field, we're able to recognize those papers. In fact, the ideal papers for ACS Nano would be those papers that are a little bit ahead of their time, right? That no one's sort of working on. It's a little bit of a crazy idea, but the result is very interesting. And those papers are the ones that are eventually become seminal and highly cited. And so we're always looking for those types of papers in ACS Nano. ACS Nano is a wonderful journal in the sense that the editors make up a nice team and community in all aspects of nanoscience and nanotechnology. And so it's the leading journal in nanoscience and nanotechnology. Our impact factor is reasonable. We're not driven by the impact factor number, but of course, if you talk about a journal nowadays, you have to mention it. It's on a good trajectory. It should go up to maybe 17, 18 next year. So so we don't artificially try to increase our impact factor. We're just looking for good, solid paper in the field that will serve the community and allow researchers to thrive. Just sort of some information about ACS Nano. We publish reviews in addition to sort of comprehensive original research articles. We also publish reviews, perspectives on cutting-edge research, conversations with thought leaders, and distinctive views about future of nanoscience and nanotechnology. So these are sort of editorials. What's really important to know about ACS Nano is that we publish comprehensive original research articles. The word comprehensive is important here. If you have a short communication, you're better off sending that to Nano letters. In ACS Nano papers, we're really looking for the authors to go into some depth on the topic of their paper. The reviews, perspectives, conversations, any sort of distinctive views are best served when authors contact an editor with demonstrating that they're interested in doing this sort of thing. The review articles in ACS Nano are scarce. We don't publish too many reviews, but the reviews should be topical and forward-looking. The reviews should serve as a paper where someone who's new to the field, perhaps a new PhD student, doesn't have lots of background knowledge, the review should serve to distill information in the current state of the art, make some conclusions, and provide some directions for the future. So it's really important to discuss the outline and the topics of the review with an editor. If you just cold submit, perhaps the framing of the topic may not be within the scope of the journal, but oftentimes editors like myself will help you to if the topic is interesting, then we can help you to formulate a really comprehensive review in the way that ACS Nano likes. So because we don't publish very many reviews, although reviews are not by invitation only, it does help to have some editorial feedback before you actually submit. Perspectives are just brief reports summarizing research or findings of particular interest to nanoscientists and nanotechnology. So again, this is not as comprehensive as a review paper, but you might want to provide, if there's a field that has multiple different directions, you might want to provide a perspective for a direction. Nano focus is something where if you're holding a workshop or a meeting or some event related to policy or education, then there's an opportunity to write a small blurb regarding that as a nano focus. But this is strictly by invitation. So if you have an upcoming meeting or if you have an upcoming event that you'd like to highlight and you think would be an interest to the nanoscience and nanotechnology community, then you can contact the editors and one of the editors, and we can discuss whether it's appropriate for the journal or not. Okay. One sort of very nice thing about ACS Nano that we do is that we publicize works. So if you feel that your work is important and we feel that your work is important, then we have a very wide reach. All of the editors have Twitter accounts. They're on various different social media, not just Twitter, but WhatsApp, WeChat, K-Talk, all of the sort of different apps in different countries. And we post important papers that are picked up by these different social media outlets. And so paper can get really noticed if it's when it's published in ACS Nano. And so there are different ways that we do this. So some of the papers that I find interesting that I edit, I will post those or tweet those out. But I can also recommend some papers as editor's choice. And these have the benefit that they're made free to read for up to 6 months, so that there's no cost to downloading it. It's without a subscription, so it's kind of like open access. We have connections to news outlets all over the world, so New York Times, various different newspapers in various different countries, and we can also incorporate different studies and different papers that we publish into different policy documents in different governments all around the world, right? So really there is a tremendous desire for the editors at ACS Nano to advertise good science, right, and seminal discoveries. There's a benefit if you're worried that I don't want to submit to ACS Nano because I want to submit to Nature because I want maximum exposure to for my paper. Don't worry about that, because we have mechanisms to reach people far and wide across the different fields. Okay, so that's sort of a brief introduction to ACS Nano. And if you have any questions about ACS Nano, please put them in the Q&A, and I'll be happy to answer them. One additional thing that I will say is that if you have a paper that you feel is important and significant, and you want to get in touch with me to see whether it's suitable for ACS Nano or not, please feel free to do that as well. Of course, I can't reply to you right away, but I'll try to do my best to look through it quickly and give you some insights into whether it's suitable, or what you might need to do to make it suitable for ACS Nano. Okay, so that's all I have for ACS Nano, and now I'll move to my technical talk. Right. So today's talk, I'll mostly talk about transition metal dichalcogenide semiconductors, but also actually, in fact, I won't be talking about 2D TMD semiconductors. I'll be talking about the metallic phases of 2D TMDs. So these transition metal dichalcogenides are something that we started working on since 2009. They have this sort of generalized formula that I think all of you, those that are working in the 2D field, will know. The formula is MX2, where M is a transition metal from group 4 to group 10, and X is a chalcogen, so sulfur, selenium, or tellurium. And it can combine these transition metals with these chalcogens to form these compounds. Now you can see that some of these transition metals are solid colored. That means that they form, if they're solid colored, they form layered van der Waals materials, which can be exfoliated down to a single layer. Some, like cobalt and rhenium and iridium compounds, are not layered. Although we can form these transition metal dichalcogenides, we can't exfoliate them down to a single layer. But in any case, we have up to 40 odd compounds that are TMD compounds, and they have very different properties depending on what combination of transition metal and chalcogen you choose. They can be semiconducting metals, etc. What we've been doing over the last decade or so is phase engineering these TMDs. So crystallographically, structurally, they can be in this trigonal prismatic, which is called the 2H phase, or this octahedral configuration, which is called the 1P phase. And so these different phases have different electronic properties. So for example, for MOS2, the 2H phase is semiconducting, and the 1T phase is metallic. And what we've been doing is we've been using chemistry to go between the 2H and the 1T phase, that is between the semiconducting and metallic phase. And so the semiconducting phase obviously has the interesting properties by being a semiconductor, so one can make transistors, one can make optoelectronic devices and so forth. But it turns out that the 1T phase, the metallic phase, is extremely interesting for electrochemistry applications, in particular catalysis and for battery applications. And that's what I want to talk to you about today. So how do we go between these two different phases? What we showed in 2009, 2010, with this first paper in Nano Letters, is that you can use chemistry to engineer the phases between the semiconducting and metallic phases. And so if you start off with bulk MOS2 powder, bulk MOS2 powder is in the 2H phase, so it's a semiconductor. And it's an indirect bandgap semiconductor because multilayers have an indirect bandgap. But if you exfoliate the MOS2 down to a single layer, then it becomes a direct bandgap semiconductor. However, to do the exfoliation, we use this butyl lithium chemistry. That is, we intercalate lithium in between the layers of MOS2, and that chemistry leads to a phase transformation from the 2H phase to 1T phase. The chemistry of the phase transformation is something that we've published quite a bit on, but very briefly, we have this additional electron from the lithium that goes on to MOS2 into the d orbital of the molybdenum specifically. And to accommodate this additional electron, there is a structural change that happens, that is from the 2H phase to the 1T phase. And you can monitor this with a Raman spectroscopy. So here, as deposited means after we've done the chemical exfoliation, we take individual sheets of MOS2 that are now in suspension, we deposit them onto a substrate and we measure the Raman spectrum. And what we see is that the appearance of these J1, J2 peaks, which are characteristic of the 1T phase. The 1T phase in MOS2 is metastable. And so if you anneal this 1T phase material to 300 degrees C in a controlled atmosphere, you can convert it to the 2H phase again. That is, the J1 and J2 peaks disappear. And so there's a sort of a control over going from 1T to 2H by simple annealing, and then going from 2H to 1T by doing chemistry. And so this gives us quite a bit of leeway in the properties that we can impart onto our exfoliated two-dimensional nanosheets. We can quantitatively work out what the 1T to 2H phase concentration is via XPS. And in the exfoliated sample, we can achieve up to 80% metallic phase. The remaining is the semiconducting 2H phase. And we can check that this 1T phase has converted completely back to the 2H phase upon annealing at 300 degrees by measuring photoluminescence. So we know that for monolayer 2H MOS2, we have a nice PL because it goes from an indirect bandgap semiconductor to a direct bandgap semiconductor when you go down to the monolayer limit with the A exciton and B exciton peak. And when we do the phase conversion to the 1T phase, we can see that the PL is completely quenched because it's no longer a semiconductor. Now it's a metal. And so I'm going to go through some of the properties, catalysis properties, and supercapacitor properties relatively quickly because I want to show you some new results that we have on using this metallic 1T phase as a cathode in lithium sulfur batteries. So one can see that so this is results of hydrogen evolution catalysis from exfoliated MOS2. That is the 1T metallic 1T phase of MOS2. So when one measures the catalytic performance of any material, one plots the current density as a function of the applied potential with respect to some reference hydrogen electrode. And so when one reports the catalytic performance of a material that's not platinum, we always compare it to platinum because platinum is the best catalyst for evolving hydrogen. The reason why platinum is the best catalyst is because the hydrogen evolution occurs at no potential, no overpotential, and it has a very sharp kinetics, right? So the reaction proceeds very, very efficiently. Of course, platinum is a precious metal, and we'd like to move away from that. So if we compare the 1T, that is the metallic phase of MOS2, we can see that there is some overpotential that is required for the reaction to proceed, and then the reaction proceeds fairly efficiently. We can compare the reaction kinetics by plotting the overpotential as a function of current density to obtain these linear curves from which we can extract what's called the Tafel slope. Okay, so the lower the Tafel slope, the better it is. For platinum, it's on the order of 30 to 35 millivolt per decade. And for 1TMOS2, one can see that you have a Tafel slope around 40 millivolt per decade. And an overpotential, that is the potential, additional potential that's required above the thermodynamic potential to split water, is around 100 millivolts. These values are, of course, not as good as platinum, but they're still very good because 100 millivolts you can easily get from the open circuit voltage of a photovoltaic, and 40 millivolts it suggests that the kinetics are reasonably good and not sluggish. The idea here is that we'd like to have a catalyst for the hydrogen evolution reaction, a catalyst for the oxygen evolution reaction, so we can split water. And so because we can obtain this sort of voltage from a photovoltaic, we can do this hydrogen evolution reaction via clean energy, that is the energy from the photovoltaic. So the way the hydrogen evolution reaction works is that you have your proton that is adsorbed onto your catalyst, which recombines with an electron to have an adsorbed hydrogen species on the surface. Eventually, if you have enough of these adsorbed hydrogen, they combine and evolve hydrogen. And so these, from the polarization and the Tafel slope curves, we can obtain the kinetics and thermodynamics of this reaction. And so I've just summarized some of the results over the years that we've reported for these metallic catalysts for hydrogen evolution reaction. And so the main point that I want to make is that if you plot the catalytic activity, that is the exchange current density, as a function of the 1T phase concentration, and I explained to you in the previous slide that we can tune the 1T phase concentration by tuning the chemistry of synthesis, but also by annealing the as exfoliated samples. And so we can tune the 1T phase concentration, and what we can see is that the exchange current density, which is an indication of the catalytic activity, increases by an order of magnitude. And this suggests that by just from going from 20% 1T phase to 80% 1T phase, that we're able to increase the catalytic activity by an order of magnitude, which is quite nice. The one thing that is always highlighted with MOS2 as a HER catalyst is that in addition to sort of its a nice catalytic performance, it's earth abundant and it's inexpensive. So MOS2 you can find in a lubricant as a lubricant to lubricate common machinery. So it's not as expensive as platinum, and it's widely available. We've also done theoretical calculations to show that in addition to the metallic phase, the thermodynamics there's also strain when you do the phase conversion, and strain plays a critical role in driving the HER reaction. That's shown by this free energy diagram. So anyway, to cut a long story short, we've been sort of working since 2013 to make good MOS2 catalysts. And what we learned is that the best catalysts are those that are very metallic and have good thermodynamics. And so it turns out that niobium disulfide is the ideal catalyst for HER, because niobium disulfide is highly conducting, and the thermodynamics of niobium for HER are quite good. And so we made some metallic niobium disulfide catalysts, and we found that it was possible to achieve very high current densities on the order of a few amps per centimeter squared. And so we then fabricated electrolyzers to actually split water, where the cathode was this niobium disulfide, and the anode, just as a reference, was platinum. We're able to show that we can actually generate hydrogen with current densities of up to 1 amp per centimeter squared. This is quite important because in order for these materials to be used as real catalysts, they have to work at very high current densities and generate hydrogen at the production scale. Okay, so that's all I'm going to say about hydrogen evolution reaction, because I want to sort of move to demonstrating these MOS2 metallic MOS2 nanosheets as electrodes for energy storage. So as I showed before, when we do the exfoliation process, what we end up with are these nanosheets that are floating around in liquid, typically water. And so then we can restack them. We can do vacuum filtration, for example, and make these very nice electrodes that are flexible. And if you look at them in an SEM, in the cross section, what you find is that these restacked sheets look like crumpled pieces of paper that have been stacked together. And just from the SEM, one can see that this structure would be quite nice for intercalation and deintercalation of ions, i.e. As electrodes for supercapacitors or batteries. Just to show you what these flakes look like, these are just sort of single layer flakes deposited on SiO2. And this is a high resolution TEM image showing that it's 1T phase. And again, the XPS and the XRD data is shown here. So again, to cut a very long story short, my student showed in 2015 that one can make very nice supercapacitors with metallic MOS2 nanosheet electrodes. So if you plot the capacitance as a function of voltage, the CV curves, we can see that these are nice square curves, and we get nice capacity for lithium, sodium, and potassium. For the protons, we can see these sort of nice redox peaks that as one would expect. And there's good sort of rate performance of these supercapacitors, and we're able to achieve volumetric capacity that's on the order of 500 farads per centimeters cube. And this is all due to the metallic phase allowing the ions to intercalate and deintercalate, and the high conductivity of the metallic nanosheets really boosts the kinetics. This narrow CV plot here is the CV for the 2H phase MOS2 nanosheets. And you can see that there's very little capacity that's also indicated here, where the 2H phase MOS2, the volumetric capacitance is negligibly small in contrast to the 1T phase nanosheets. What this plot shows is that it is in fact the positive cations that are intercalating and deintercalating. So there's some question that because in this plot we see that the anions are all the same. Are we getting this performance because of anion intercalation and not cation intercalation? The way to prove that is that you can keep the cation the same and vary the anion, and you can see that the CV curves are almost identical, suggesting that it's the potassium that intercalates between the sheets of 1T phase MOS2. So one other thing that you can do then, so because we have this large amount of intercalation and deintercalation of ions, there is an expansion and contraction of the MOS2 electrodes, and we can use this expansion and contraction of MOS2 electrodes to make actuators. So what you're seeing here is a freestanding MOS2 1T MOS2 film plated with gold, and by applying some voltage, we're able to intercalate. This is all within an electrolyte. We're able to intercalate and deintercalate the ions, causing this cantilever to curl or uncurl because of the expansion and contraction of the MOS2 film due to intercalation and deintercalation of charged cations. And so we can correlate the movement of a cantilever directly to the CV characteristics of the cantilever. So we can prove that this movement is happening due to expansion and contraction of the MOS2 film due to intercalation and deintercalation of the ions. And so then you can be a little bit clever and make an actuator system that's capable of doing work. So my student designed this Bimorph Actuator where without any moving parts, so he took a strip of polyamide and he made some strategic cuts and he put MOS2 film in specific locations such that upon intercalation and deintercalation, it would contract, the top layer would contract this way, the bottom layer would contract this way. And this way, the actuator is able to expand and contract. And then he attached a weight at the bottom of this Bimorph actuator, and through intercalation and deintercalation of the MOS2, he demonstrated that this actuator was capable of doing work that is lifting the weight up and down. In the paper, we have some videos to show how it works. For any case, this is a sort of an example of converting electrochemical energy to mechanical energy. And when one looks at the weight of the active material, around 1.6 milligrams, and the weight of the work that's being done, that's 265 milligrams, one can see that these electrochemical actuators are quite strong in the sense that you're able to lift a weight that is 150 times more than the weight of the active material. So so in addition to sort of batteries, one can also design and batteries and supercapacitors, one can also design these actuators. Okay, so in the last part of this of the presentation, I will just talk about our latest work. This is not published yet. It's a work on using these 1T phase MOS2 as cathodes in lithium sulfur batteries. So we're part of this Lystar program, which is funded by the Faraday Institution in the UK. The Faraday Institution was started to enable the UK to transition to electric vehicles, and so one of the consortium in Faraday Institution is the Lystar Consortium. It's the largest project on lithium sulfur batteries in the world, as far as we know. And so we are responsible for this work package one, that is to design new cathodes for lithium sulfur batteries. The main problem, as many of you will know, in lithium sulfur batteries is that you have the formation of these polysulfides, and shuttling of polysulfides leads to a short lifetime of the batteries. Also, the overall performance of lithium sulfur batteries using the traditional cathodes, which are typically porous carbons, has not been satisfactory. So this lithium sulfur battery, in principle, if you can eliminate this lithium anode, it could be quite safe, and the chemistry has the ability to achieve high capacity, energy density, and power density. And so we've been looking at new ways of incorporating new ways of designing the cathode. So conventionally, the cathode that's used is some porous carbon plus the electrocatalyst, and on the porous carbons, and sulfur is loaded. You can't use sulfur directly in lithium sulfur batteries because sulfur is non-conducting. So you need to load the sulfur onto some conducting framework, right? So porous carbon is typically used, and that can be activated carbon, reduced graphene oxide, graphite, carbon onions, and so forth. Oops, sorry, let me just go back. Yeah. The carbons are used as conductive scaffold and as sulfur host. But from a device perspective, when you have porous carbon, you have to use quite a bit of electrolyte. That is, the electrolyte should penetrate all of the pores. But ideally, we'd like to have as low of the electrolyte to sulfur ratio as possible, because if you incorporate lots of electrolyte, you increase the weight of the battery. So we'd also like the electrolyte to be wet the electrode very well. We'd also like the overall resistance between. So when one loads these electrocatalysts onto porous carbon, the electrocatalyst is typically a manganese oxide. It's some oxide-based catalyst, and it's loaded onto porous carbon, and there's an internal resistance that between the catalyst and the porous carbon. So we'd like the electrode itself, the framework on which we put the sulfur itself, to be electrocatalytically active, and that's where this 1T phase really comes in handy, because it's conductive. It's not porous. The overall surface area is only of the order of 9 meters squared per gram. It's highly wettable to most electrolytes, and it's a catalyst, as I just mentioned. And so the idea here is to use 1T MOS2 as the scaffold to host the sulfur. And so I already showed you how we do the preparation. So let me show you some of the properties that we achieve from these 1T phase MOS2 cathodes. They're really sort of extraordinary. So first, we made some coin cells where we really were only testing the properties of the 1T phase. So if one looks at the capacity curves, one can see that you see these very nice plateaus. All of these sort of plateaus point to the different polysulfide reactions that happen on the cathode in the lithium sulfur battery. And so we get these very nice characteristics, very good rate performance as well. But when one looks at the overall capacity of these coin cells, it's extraordinary. It's on the order of 1400 milliamp hour per gram, suggesting that we have over 85% sulfur utilization. There's very good rate capability, and there's 91% retention over 500 cycles. But it's all very good, but the problem is that with coin cells are not really. So if we compare sort of our data with references, one can see that these 1T phase MOS2 cathodes actually work extremely well in terms of the volumetric capacity and the amount of sulfur loading. They're amongst the highest that have been reported, with electrolyte to sulfur ratio that are less than 4 milligrams per centimeter squared. So it's really encouraging. And the main reason for this improved performance, we believe, is that because the 1T MOS2 it has sulfur in it, the interaction of the sulfur with MOS2 is quite strong. So we have a large adsorption of the polysulfides that are formed in the reaction at the cathode, and that's borne out by this adsorption data, where we place the different polysulfides in the solution with our 1T MOS2, and we can see that these 1T phase MOS2 has the highest or the lowest absorbance. That is, that all of the polysulfides are now adsorbed onto the cathode. And we can also show that the 1T phase MOS2 has the lowest internal resistance and a very high catalytic activity for the sulfur reduction reactions with specific polysulfides. So in any case, the coin cells are really good, but what I want to highlight and show here is this results from our pouch cells. So pouch cells are the sort of practical batteries, practical devices that one needs to demonstrate that a material is good as a battery electrode. And so we fabricated several of these pouch cells by hand. So my postdoc has done everything by hand. So here the cathode is our 1T phase MOS2 that's been loaded with sulfur. We use the standard electrolyte, and the anode is lithium. And so when we test these pouch cells, we again obtain extraordinary properties. We have very high aerial capacity, and we make our devices show a total capacity that is at the amp hour scale. So this is quite rare in a laboratory, in an academic laboratory, to make devices with amp hour capacity and energy density values of 402 and volumetric density of 721. These are among the best performing pouch cells made in the Lystar Consortium. So it's quite exciting that this 1T phase MOS2 works so well as a sulfur host for lithium sulfur cathodes. And the cycling stability is also quite good. It's over 85% for over 200 cycles. So there's a lot of potential for using these metallic 2D TMDs for different types of batteries, lithium sulfur batteries, perhaps even lithium ion batteries. If one sort of thinks rationally about the challenges facing the different devices, then one can sort of specifically target those challenges with metallic phase of these TMD compounds. So that's all I have. So I will thank you for your attention and leave some time for questions. But I'd like to thank my research group. The lithium sulfur work is done by Jungnan Lee. A lot of the catalysis work was done by this Korean postdoc. She's now a professor at Kyunghee University in Seoul. And she did a lot of the catalysis work. And Ishmael Sami is doing a lot of the supercapacitors and batteries work as well. So thank you for your attention, and I'm happy to take any questions.
Yeah.